Now let's talk a little bit about page protection flags. Page protection flags allow us to specify for each page what you're allowed to do with it, whether you're allowed to read it or write it or execute it. So each page can have these different rights or permissions, which are typically read, write, and execute. And let's take a look at how this works out in our program's virtual address space here under Linux. So if you don't have permission for what you're trying to do, the hardware in the operating system will cause you to crash. You'll get a memory protection or a segmentation fault, otherwise known as a seg fault, and the OS will kill your program. So the kernel space up here, you have no permission to it. If you try to read this data, write this data, or execute it, it's just going to go ahead and crash your program. Same for this I/O space down here. Now, the stack and the heap, these you have permission to read and write. You need to be able to edit this data and access it, but you don't want to be able to execute data in here. So you should never be able to run code from your heap or stack because this is just for data. If you're running code in here, it means either your program's messed up or somebody's trying to hack it. So the execute permission isn't available for the stack and the heap because it is basically for a security reason. However, we do need the ability to execute down here in the data and text. This is where our program lives. So we need to be able to execute this code and read it, but we don't want to be able to write it. We don't want to be able to change our program while we're running. We want to keep our program the same when we're running it. There's also another really cool thing we can do with virtual memory, which is called copy on write or COW. So copy on write tells the operating system and the hardware, if the program writes to this page, don't let it do that. But first, the OS is going to make a copy of the page to a new page, update its page table entry, and then allow the program to modify it, but now it has its own private copy. So if we use this, it allows us to share data as long as we don't modify it, but as soon as we modify it, we get our own copy. So if we look over here, our libraries are probably going to be copy on write. So if there's any shared data that we have here that we want to change it, as soon as we go in and write it or change it, the OS is going to give us our own private copy of that page so we don't mess up other programs. But as long as we don't change it, then we can save memory space by having the same memory for all those pages. So copy on write allows us to say, let me share this until I change it. And as soon as I change it, make me my own private copy so I don't change anybody else's copies. Now, how do we actually do this? Well, here's our page table, and we're just going to add some bits to it for permission. And this tells us for each page what we're allowed to do. We can read, write, or execute, copy on write, read, execute, or nothing. So if you try to do something which you don't have permissions for, you get a segmentation fault. So here, if I try to access this page in any way, I'm going to get a crash because I don't have permission to access this page. If I try to write to this page here, I'll get a crash because I only have permission to read or execute it. I don't have permissions to write it. So here's a question about memory protection and protection flags. What are reasonable page protection flags for the page FFFF to allow these two programs to share the data? Well, read-only or copy on write are reasonable. And the reason for this is read-only will allow both programs to share the data, but not write to it, so they can't corrupt each other. And copy on write will make sure that if one of them writes to it, it gets its own copy and doesn't corrupt the other one. So if these pages were copy on write, and program 2 went to write to this page, the operating system would copy the page first, and then give it its own physical page number here so that it didn't write to the physical page that program 1 was looking at.